Hello, my name is Nakangutedi, Teddy, Computer Science Year 3, Makerere University, and I'm going to present about our computer graphics project under the topic Multi-Agent Visual Storyboarding for Accelerated Refugee Education, Computers-Based Content Authoring. So this project is not just AI, but it fundamentally computer graphics and visual programming system for education. So the visual storyboarding clearly indicates graphics pipeline, procedure scene generation, and even animation-ready assets. And then the multi-agent part means that the system uses different specialized modules, for example, a curriculum map of text processing, storyboard generator, anime generator, and even a video composer. So basically, we created a graphics-driven content authoring tool, not just a text generator. And then under this topic, we have some keywords. One, we have computer graphics, which is a field of computing that focuses on creating, manipulating, and even displaying visual content using computers. So it involves generating images, animations, visual simulations, using mathematical models and algorithms, let's say 3D modeling, rendering, animations, and more. And then we have visual programming, which is a programming tool where developers create programs using graphical elements such as like diagrams, flowcharts, and in this case, we may encounter features like icons, blocks, connections, and more. So we have another one, which is competence-based curriculum, which is a learning approach that focuses on mastery of skills and competences rather than just covering content. So here, students progress by demonstrating their understanding and ability, not just the time they spend in class. So we have another one called generative learning technologies, which is basically AI-powered tools that create new educational lessons or content, for example, quizzes, lessons, explanations. So these ones help like personalize the learning by adapting the materials to every learner's level. So then we have interactive storytelling, which is a method that uses stories with user participation to enhance engagement and learning. So here learners can make decisions that may affect the story's outcome. So this improves their critical thinking and even their retention. And then we have multimodal AI, which are AI systems that combine multiple types of data. That could be text, images, audio, videos to understand and generate maybe richer outputs. Then we have refugee education, which is an education type designed to meet the needs of displaced learners who face barriers like interrupted schooling, sometimes language barriers or challenges, and also even sometimes lack resources. And then lastly, we have vision language models, which are just models, advanced AI models that link visual and textual understanding. So this one, they can interpret images, describe them, let's say in words, or even generate images from text. And then that brings me to our next slide. So this one has contents of our presentation, basically. Then when it comes to the background and introduction, so first of all, over 387,000 refugee children are enrolled in accelerated education programs with challenges like limited resources, language barriers, trauma gaps. And then some of the gaps in these accelerated education programs are that they have like teachers have or educators have to create graphical and learning media manually, let's say like drawing with bare hands to make students understand, yet to some extent they lack skills in like maybe 3D modeling, visual programming, and maybe like things like content designing. So you find that it becomes a challenge with visual learning content, which is an essential tool or key in the computers-based curriculum. And then teachers cannot like manually create graphics, even animations, because they require these skills that we talked about earlier. And then the fact that they lack resources and those resources that they have, maybe like books, are mostly outdated, adds on the gaps and challenges. So this is where our system comes in play, and it introduces an AI-driven multimodal content authoring system, which solves these issues by automating computer-generated images, generative graphics, speech, and even visual programming to generate CBC aligned lessons, let's say, animations, and even storyboards. So basically, computer graphics makes abstract competence-based curriculum competences visible, concrete, and even engaging, so which is essential for the refugee learners. And then we may ask ourselves why graphics. One is to enhance understanding. This is in the sense of converting complex data, concepts, or even the environments into clear visual representation. Then we may also think about improving engagement. So this is because like visual rich content, like maybe images, animations, simulations, keeps the learners like, or maybe even the end user like more engaged than it would be with the text. And then the other thing is that it supports realism, like through enabling realistic modeling, rendering, and animation, which is useful in education. And lastly, the better communication in such a way that these visuals convey information faster and more effectively than maybe text alone. So allow me proceed. So then when it comes to the related works, we're able to review some papers basically in recent years, looking at different models, contributions, and architectures, where most of them were to do with taking in text, images, and then generating captions, description, images, or even videos. So we also looked at the problems they encountered, which included memory constraints, like some models needed higher compute, quality issues, among others. Then most of these papers are related to our project as they were in the same way grounded in graphics-based learning systems, generative media technology, vision language, AI, and even multimodal storytelling. So we extended these existing systems or models by adding automated graphics, generation and culture adaptive visual programming. Then when it comes to the problem statement, so for the problem statement, like I said earlier, like very many refugee students are enrolled in accelerated education program, but then they lack access to high quality localized learning materials since these materials are in most cases outdated, linguistically misaligned, or even unavailable offline. So because we know these children come from different countries, speaking different languages, which becomes also a challenge. And then these refugee settings lack devices or even internet sometimes. Remember, accelerated education programs are it's just a flexible learning program designed to help these learners who have missed like maybe part of their schooling or even never enrolled that will catch up with the standards of the curriculum in a short time. And then on the side of computational problems, one, we have curriculum aligned content generation. So, which is to do with generating lessons that are mapped to Uganda's competence-based curriculum, ensuring pedagogical accuracy, competency alignment, and then maybe structured learning. So another one, we look at multilingual support, which involves generating or integrating multiple languages to promote language inclusivity and better comprehension. Then we look at cultural adaptation, which is basically where visuals and narrations reflect culture, enhancing engagement and relevancy. And then we also lastly look at offline on all low bandwidth optimization, which is which deals with low resource deployments, enabling offline learning, like in connectivity limited refugee settings, which we are targeting. So the problem lies in how we achieve those computational aspects. Then when it comes to the research objectives, so we ask ourselves questions. One is that we ask ourselves, how can graphics-based content authoring framework support CBC aligned learning in refugee education? Then what methods can generate multilingual, cultural, adaptive, interactive learning modules that function offline or even in low bandwidth settings? Then how effective are AI-generated graphics and interactive content in improving learners' engagement, comprehension, and even retention? And then how can open access visual learning objectives and templates be designed for scalability and reuse by educators or even like the NGO in fragile systems like the refugee settings? So these research questions influenced our research objectives, which are to develop an offline fast modular graphics content authoring framework for competence-based aligned learning modules, then to create animated and interactive learning modules using lightweight platforms. Another one is to evaluate learners' engagement, comprehension, and retention in education settings. And lastly, to produce open access visual learning objectives and templates for these educators in those settings, and then the NGOs to adapt and scale. So altogether, these the decisions and outputs of our projects were based on these objectives and questions. So then, when it comes to the contributions, this is what we were able to do. So we developed a system that to generate structured lesson scripts for CBC aligned topics, and we implemented the evaluation framework for assessing script quality, the topic alignment, and also resource relevancy. So we also prepared a structured CBC aligned topic dataset for lesson planning and automated content generations. And last, we provided data-driven insights into script coherency, topic coverage, and even engagement to guide future multimedia lesson development. And then that brings me to our methodology. So for the architecture, first we have input. We have the input stage, which is for the text input that is expected from the user, and that could be the teacher or maybe the students who want to use the system. Then we must make sure that this prompt is CBC aligned, and that is why we pass it to the curriculum mapper. In our case, it's the all mini LM, which comprises of a transformer encoder that produces semantic embeddings, a similarity layer that maps the curriculum outcomes to the topic prompts, and then finally we have our output as a curriculum aligned prompt. So that output is then passed to the story and script generator, that is the Phi3 mini, which does the token embeddings and then positioning coding, passing the output to a multi-head self-attention, which is a decoder and a decoder only transformer. So here we obtain a script draft that is passed to a culture grounding layer that adds the culture content generation. Then it generates a culturally augmented script that is then sent to a storyboard generator, that is a Stable Diffusion XL. So this one comprises of a text encoder that encodes script lines that are then passed to attention decoder, male spectrum, which is called a tacotron, and a vocoder that produces a web file or a narration audio file. That is where we use our Google TTS model. And then the encoder script lines that are generated, then they are passed through the unit denoiser that comprises of an encoder, and the downsamples the latent. Then it also has a cross attention that injects text features into the decoder. That injects the text features, and then the decoder that upsamples the latent to a clean image, and then it passes it to the VAE, which is a variation autoencoder that converts this latent to image processing to an image, and then it processes a culturally relevant storyboard frames. Then after that, we also have a lip sync encoder, which has a face encoder for spatial face features. It also has an audio encoder for speech features, and then a syncnet discriminator for aligning the lip motion with speech. So their output is passed to a generator and a discriminator module that produce synced face video clips. And then finally we have the storyboard frames that are generated earlier, the narration audio, and even the lip synced video clips. They are sent to a video, the lip synced are not videos, they are just lip sync clips. They are sent to the video composer, which is the MoviePy library that we use in this case, that combines them and aligns the visuals and voice using a timeline sequencer, and then renders transitions using a transition engine. And finally, we obtain an instructional video. So that is it with our methodology architecture. So these are basically individual architectures of the models, individual model architectures for the models that we are using at the different steps in the overall architecture. That is Stable Diffusion Excel, Mini LM, Google TTS, Wave Tulip. Then that brings me to our data set. So for the data set, we're using a data set that was extracted and organized by the research team from Uganda's mathematics competence-based curriculum under the accelerated education program. So it basically has 17 entries, 12 features, and it is basically for level 1, term 1. Then the target value is typically competence, which defines the skills or ability that a learner is expected to acquire. So some of the core columns include the subject, level, terms, topic number, topic title, and duration. And then we also have pedagogical content fields, which includes the competency, learning outcomes, teaching, learning activities, Bloom's tags, and more. So and then for the Bloom's tags, it's basically from the Bloom's taxonomy, which are levels of cognitive domain, which are used to define learning objectives and also guide progression from lower to higher order thinking skills. So they include maybe remember, understand, apply, analyze, evaluate, create, value, etc. And they're represented by letter abbreviations in the curriculum. So when it comes to our exploratory data analysis, we're able to visualize results from it to help us understand the data that we're working with and give us insights as we continue to use the data. First, we visualize learning outcomes. Learning outcomes tag frequency, which shows how often pedagogical tags appear across all learning outcomes. So this gives us an insight on which competencies are commonly tagged, because it is a very crucial aspect when it comes to our project. And then we also have outcome per count, which displays the number of learning outcomes assigned to each topic. So this gives us an insights about the topics with maybe many outcomes that may require deeper coverage. And then we also visualize activity count per topic, which illustrates the total number of suggested teaching and learning activities associated with each topic, which gives us a quick comparison of how the activity dense of each topic is. And then we also visualize the tag concurrency heat map. This one visualizes how the different learning outcome tags appear together within maybe the same outcome, revealing the pattern of how competencies are combined. Then we also visualized the duration outcome, comparing the duration allocated to each topic with the number of maybe associated learning outcomes. So this gives us an insight on how allocated time aligns with the quality of content that's to be produced. And then lastly, the narrative density per topic, showing the narrative density of each topic, giving us an insight to the text length of the data that we are basically working with. Then when it comes to the results, so these are some of the videos that we are able to generate from the pipeline. And then first we see that the images, like for this first video, they're not perfect, they're not yet there. Let me play it a little.
Welcome to our exploration of number bases. Today, we'll learn about the different ways numbers can be represented.
And even the voice is still lacking. So we have very many results, like videos, visualizations from the different
Explain
models and visual programming. Then, so for the video, for the first video, already discussed earlier, the one I showed first, the models that we realized that the models really need further fine tuning to produce better visuals. And then so as we were advised to use reinforcement learning, we tried, but not yet successful. But then we intend to use its component, which is a direct preference optimization, which belongs to the preference-based reinforcement learning that trains models from pairs of preferred versus non-preferred outputs. So we are at the point of generating scripts because it requires us to have a number of scripts, which we will categorize as accepted or rejected. And then we use our scripts generator for the algorithm, in this case, to generate those multiple scripts. So allow me to proceed to the model selection. So when it came to the model selection, we chose models depending on our goals and objectives, focusing all considering their purpose, key, strength, and also limitations. So this table gives an overview of these models, of why they were selected for our pipeline. For example, some were fast, lightweight, efficient, scalable, which would work for our system. And then for the video demonstration, first of all, for the IP assets, we have some the custom curriculum dataset that we generated, overall pipeline design, education use framing, the integration design, all base lesson scripts and more. And then we have this layout for our deployed system. I may not have to demonstrate it here because it for now takes a bit of longer time. So we deployed it on Hugging Face, where a user inputs their text prompt, then click submit to generate a video, which is downloadable or shareable via a link. Yeah. So then when it comes to the limitations, first, like I showed you earlier, the generated images did not fully capture the text, the exact meaning of the script. So basically are going to fine tune the stable diffusion with education and cultural images to improve textual accuracy. Then the voice generated wasn't in line with the local context. So we want to also adapt the Google TTS with local voice examples. Then the generated images also lacked motion. That is what we want to integrate motion generation models. And then we have limited resources. We always crashed with GPUs and what. And for that, we use the clearing memory after each output. Basically, this is how we're able to work with it. But after fine tuning, we're going to do some pruning and all that. And allow me proceed. So when it comes to our feature works, we want to transform the static images into animated sequences while maintaining sequence layouts and video diffusion models. Then we want to conduct pilot studies with our teachers and learners to measure the comprehension, engagement, and also retention. Then we want to apply a quantization, pruning, and what after fine tuning, like I said earlier, to work on the memory issue. Then we want to also include regional languages like the Swahili because the students come from different countries. So to conclude about that, the pipeline was successful in demonstrating how combination of all this image, audio, video with this multi-agent system really help to create videos that are aligned to Uganda's knowledge-based curriculum. However much the videos are not yet in motion. And then there's some of the references of the data we're able to gather and use. And then we'd like to thank our supervisor, Mr. Galiwango, and then the examiner and us, the team, everyone in the team members, and all those who took part in this to help us reach this far. And we hope to improve this even better and take it up as well.